Hello everyone, my name is Joseph Boy Ukeme and I'm here to present the workflow for data-driven fault detection and diagnosis in buildings. And the co-author of this paper is Professor Gabriel Weiner and we are from Carleton University. So the first step is the motivation for this work, right? So basically, fault detection and diagnosis is important in buildings because components fail as a result of physical damage, deterioration, inadequate maintenance, and poor quality, right? And in buildings, the consequences of this failure could be catastrophic. And generally, we don't always have control of the design of the control system in buildings, right? So for example, in retrofitting old buildings, we can't do anything like that, and it might be useful to use data, right, to detect faults in such scenarios. Also, buildings generate lots of data. Data can reflect the actual operation of buildings, and the knowledge we gain from data can be useful for detecting faults, right? So that's why data-driven fault detection is useful, right? And we notice from our research that the quality of the data-driven fault detection methods depends on the quality of the data. And then we notice in our research that there are a few resources available on how to properly collect data from buildings. That's why we're proposing this workflow that tries to address some of these challenges. So the workflow for data-driven for detection in buildings as follows, right? We start with the data collection, after which we go through a process of data understanding, and after that we go through the data preparation or pre-processing and analysis. Then we go through the data-driven modeling, and after that we deploy the fault detection models in the building. In this paper we covered the first four steps, and this is for future work. So the first step is the data collection, right? So in the data collection, to properly collect data, we develop this framework, which we call the data collection framework, right? It shows the different ways in which data can be collected in the building, right? Data can be collected through simulation, and in collecting data through simulation, we have to use some simulated fault injection to cover for faulty data, and also through the operation of the building or a model, which is a physical model of the building with fault injection, we can also collect data. And then if we have some mechanisms or facilities to record information from the building, we could collect metered and sense data. We could collect user and operator reports, and we could collect fault logs, and we can aggregate all these data into historical building data. And then after we get historical building data, we need to perform some data labeling, right, and some ground truth validation to actually tell what is a fault and what is not a fault, right? So this process is important to go through on the historical data. And after collecting all this, we put them together into what we call the fault detection data in a database or in whatever format that is available at the time. One useful thing to note here is that you would probably not have data from all these sources, but the advantage is that if you could always simulate your building systems to generate data to develop your data-driven models, and later on you can tune them when you get more data from the other sources. So one aspect of data collection that is important is that it satisfies some data requirements, and we developed this data requirement template. So you need to have a description of the data, basically tells you, well, how was this data collected, what information can we obtain from data that we have collected, and when you look at the data, you need to check the data points, right? So the data points must include relevant features, right, for fall detection and diagnosis, and it should have been collected for long enough to cover the building operating range. So basically, if you're measuring, for example, temperature, you want to have data in temperature for both the winter and the summer so that it covers the entire operating range of that temperature measuring device, right? And also you want to make sure it gets some data that describes faulty situation as well, right? And then it should also obey standard rules, right? So the number of data points, for example, should be at least 10 times the number of features. Another thing to look at in the data requirements is the fault input scenarios, right? This should be clearly defined with the types and the time, right? So for example, fault type, fault intensity, fault injection mechanisms, how was the fault injected, the measurement frequency and the duration, right? These are things that will help us in developing our models, right? And the next step is the target. So we want to know what the kind of fault it is, right? So we need to know the ground truth information, what is faulty and what is fault free, and what kind of target it is. So we went through the data collection process on a data set that we obtained from the Pacific Northwest National Laboratory for a simulation of a large office building, right? So the model was developed using two simulation tools, Energy Plus and Dymoller, and we looked into the data we got, right? They had over 272,000 data points and 18 columns of features. And then the data was collected for a period of 1 year, right? So you can see collecting temperature data for a period of 1 year kind of covers the operating range as expected. And then the fault input scenarios were defined, right? So the fault type was the outdoor temperature bias, and the fault intensities were timestamped. So like a normal measurement of temperature is X degree, the deviation from X, right, were defined as faults with varying intensity, right? A 1 degree deviation wasn't as intense as a 2 degree deviation and wasn't as intense as a 4 degree deviation, as can be seen in this heat chart. And then the fault duration lasted for about 12 hours. And in this case study, the target variable, which was the fault, was binary, with 0 representing a fault-free situation and 1 representing a faulty situation. The next step after data collection is the data understanding. And the objective of this step is to understand the attributes of the data and identify the features, right, the key features that will help us make informed decision on whether or not fault detection and diagnosis is useful with this data set. So we need to study the data to answer several questions. Some of the questions include what kind of data it is, what does it contain, how can it be described, what are the features, what is the target, how relevant is this data to fault detection and diagnosis, and are there any ethical concerns? And basically at the end of this stage we can decide whether or not it is a wise decision to adopt an approach, a data-driven approach for fault detection and diagnosis. So, for example, in our case study, right, we looked at all the features and the targets. We're able to plot them. We're able to look at the maximum, the minimum values, if it covers the operating range and how it does that. We check the number of records. We see how useful it can be for fault detection. We did not have any ethical concerns. And after looking at these plots and the data, well, we came to the decision that, okay, this data could be useful for fault detection and diagnosis. And after that, the next thing is the data preparation or pre-processing and analysis, right? So basically at this step, you have to check that your data is good. And if it's not good, you have to make some steps to clean the data, right? So you have to check the data type, and you probably need to do some conversion. You need to check for uniformity, plotting the data set like we did earlier can help for that. You need to check for missing values, duplicate entries. You need to check for outliers, right, to ensure your data is clean and ready to be used. Then we need to do some exploratory data analysis, right? So we have the univariate analysis where we look at one variable at a time, helps us understand the variable and how we can use it. Then we do a bivariate analysis, right? So here we check the correlation between variables, right? And in some cases, if we have multi-collinearity, we might not be able to use certain models. So that's why it's good to do some bivariate analysis before we proceed to modeling. So the next step in the workflow is the data-driven modeling, right? So the modeling has a few steps that we've summarized here. So we specify the targets, right, which we define the fault. We specify the inputs, which are the predictors, and then we partition the data into the training and testing set, right? The training set is what we use to train the model, and the test set is the part of the data to test the trained model. And after that, we correct for imbalance, right? Because generally we don't have so many data points for false, right? Because we expect the building to operate normally. So we need a method to correct for imbalance because unbalanced data sets affect model accuracy. Then we choose the model, right? So based on the understanding of the data, we can define the objective for the fault detection. And if, for example, we have a binary target, we know we're going to try to use a binary classification model. So we choose the model based on the FDD objective. And after that, we can evaluate our models based on, certain metrics, right? So for example, accuracy or misclassification costs. That means, well, how well does it detect false positives or false negatives, right? Do we have a lot of that? And depending on the objectives, we might want to rule out all those things. So these are methods to evaluate our models, right? This is summarized in this chart below. So we get the fault detection data. We select the target, right, where we say, okay, this is what we're trying to predict. We do some pre-processing to clean the data. We partition the data into training and testing. This is the technique for correcting imbalance. And then we develop our models. We evaluate the model results, and then we decide on the best models for our objective. So this is how we split the data. For example, in our case study, we split the data using the 70-30 rule. 70% of the data was used to train the model, while 30% of the data was used to test the models. To correct for imbalance, we use the smooth technique, which is a synthetic minority oversampling technique, right? So basically, the first step is to decide how many neighbors of a sample that we would compare with in order to generate a synthetic sample, right? So in this case, we pick the case equals to 4, means we compare with 4 different neighbors. And when you do that, you're going to calculate the distance, which is the difference between the sample and its neighbor, right? And that gives you the difference value, DIFF. Then we multiply it by a value, random value between 0 and 1, known as the gap. And then we add it to the original sample. And when we add that to the original sample, we will get a new synthetic data. And then this is how we can increase the data in the minority class, right, to correct for imbalance. So in case of our fault detection and diagnosis, the amount of faulty data that we get, we can oversample it using this method, and we can get more data samples to correct for imbalance. So after correcting for imbalance, we chose the model according to the objective, right? So in this case, it was a binary classification model. So we had different options, and we picked the k nearest neighbor and the logistic regression model. And in training the models, we had to adjust the model parameters to allow it learn from the data set. So each of these has a unique way it's done. And then we did that to train the models. And then the next step is to evaluate it. So in this paper, we evaluated those models based on accuracy, right, and predictor importance. We could also have used some other methods to check, right, like misclassification cost, right? And here we can see the logistic regression had 85.7% accuracy, and the k nearest neighbor had 96.58 accuracy. So the k nearest neighbor performed better than the logistic regression. And in looking at the predictor importance, you can see that the outdoor air temperature and the outdoor air control signal were the most important predictors for the target. So in summary, fault detection and diagnosis in buildings should not be random. It should be carefully planned from the building design to its operation. The data collection strategy should start early and should be properly done to ensure that the data collection is useful for FDD. The importance of simulated data and simulated fault injection is being highlighted in the data collection process. And we know that simulation is very important in handling imbalanced data. So we use synthetic data to handle that. And even when you don't have all your data in your building, right, simulated data can help you develop your models quickly while you can tune them when you get access to the physical environment. Thank you for listening.